So in this video, we're going to talk about mods 4.6 and 4.7. First, we're going to start with 4.6, which is about compounding periods and the compounding interest formula. When we talk about the word compounding period, it is the interest rate divided by the annual interest rate by how many times per year that interest rate is calculated for the bank. And we will go over what that means. It's not quite the same as our growth factors, but it will look very similar as we go through the equation. So let's jump in and do an example. Now it says here, you decide to invest $1,000. You have three choices of investment accounts. Each account advertises an 8% interest. Now the first one says it's 8% interest compounded annually. And the second one says it's 8% interest compounded semi-annually, or twice a year, or every 6 months. So let's complete the table for each. Now it says here, what is the interest rate per compounding period? That would be 8%. Remember, that's the decimal 0.08. So our initial value was 1,000. If you go up by 8%, or if you multiply that by 1.08, so 1,000 times 1.08, we get 10,080 at the 1 year mark, because they've kept our 1,000 there. They've given us $80. Now, if we use year 2, we had that 1,080 sitting there all year. We multiply that by 1.08. We get $1,166.40. So the actual formula, remember, is always our starting amount, our interest rate, or our increased growth at any particular time t. So in the 2 year mark, we have that $1,166.40. Now let's compare that. Oh, I'm sorry. So the annual growth rate for this is 1.08. Okay. Now it changes if the terms of our account changes. So if they say that we're getting 8% interest compounded semi-annually every 6 months, it's different. So we still have at time 0 $100 or $1,000. I'm sorry, but this time at year 6 months, half a year, our yearly interest rate of 8% gets cut in half. It's 4%. And so we would do 1,000 times 4%, 104%, or 1.04. And we would end up with $1,040. So in that 6 month period, they give us half the interest rate. So that would be 4%. So let's keep doing that. Now at year 1 mark, they've done it again. So now we're going to take the 1040 times 1.04, and we get 10,081.60. Now if we compare that with our original amount, it is $1.60 more. So we've actually gained money because we got interest on the stuff that was there for 6 months. And then if we do it again, 1081 times 60 times 1.04, we get $1,169.86. Guess what? This time we're about $3.46 to be exact, ahead of the other. But how do we set up the formula? Because if t is years, we are doing something every 6 months. So how do we account for that? Well, think about the fact we've said it, if it is 2 units that we've done it, that our rate gets calculated twice. So now that's just 2t, okay? Now, you could technically square that number. You get 1.0816, which is bigger than that 1.08 we saw up above. And we could rewrite it in terms of t if we wanted to, okay? So we could rewrite this as 1,000 times 1.086. I've just squared that 1.04. It's actually 816. And then rewrite it so it looks a little more like this one. And then we can compare the two, and we see that we do indeed get more money. And so the answer here, the growth factor for 6 months is 1.04. But if they wanted the growth factor for a year, we would have to square that. That's where that one comes from. Okay. So technically, anytime you go into a bank and you are looking at what they've offered you, or if you're looking at a comparison, do a few calculations to see where you would be at. But the more often they compound it, if it's monthly, that's going to benefit you compared to even 6 months. So the more often they give you the interest, they put it in, now they've calculated the interest off the interest, okay? So now if you could roll down, please, to this. And this is going to be our formula. I'm going to write it bigger to the side here. A equals P times 1 plus R over N and T. Okay. So A is our final amount in the account. So that is our ending, our total in the account. T represents the number of years. P represents that initial value. Remember that initial value always sat out in front. N represents the number of times they are in compounding interest. So if they say annually, that's once, semi-annually, twice, monthly, 12 times, daily, 365 times. And R is going to represent the interest rate. Make sure that you have that as a decimal instead of a percentage, or it might, not work for you, okay? So now let's pull apart the equation and let's see what it means. If we just focus on the inside of the equation right here, that inside stuff is a growth factor for one period of compounding. So if they talk about monthly, that would be what happens in a month. If they talk about yearly, that's what happens in a year. Because we took that rate, you'll notice, and we divide by the number of compounding periods. Now let's take a look at B. What happens when we put that power on there? Well, if it's compounded twice, that would be a 2. If it's compounded 4 times a year, that'd be a 4. And so what this does is this changes it immediately to the growth factor per year. So it kind of changes the formula to work nicely for a year. That's called the annual percent yield, how much you're getting in a year's time. Then you'll notice the formula has a little t on it. So you can see here, let me move this down so we can have everything in one spot. But there is a t right here. So what happens when we put the t on it? Well, that just allows us to find the growth in t years, whatever that happens to be. Maybe we're looking for how much it's going to grow in 5 years, 10 years, 7 years, 8 years. And then this gives us the final value of our account. Sorry about that. Sometimes my spelling troubles come out. Our final value of our account, since it's that initial value times the growth rate per how many years we want. So that's how the formula ended up coming about and working. But you do need to know what this formula is. You do need to know what all those pieces are as we go through it. And then we are going to jump down now because of time. Please, if we could, jump down all the way to problem number 5. Okay, so let's jump to problem number 5. Problem number 5 says a deposit of $5,000 is made into an account. Okay, I'm going to write that formula from before. F of x, or A, equals P times 1 plus R over N to the NT. Okay. Now, we already know if it says that $5,000 is in our account, our P is 5,000. Okay. Our interest rate is 5%, so our R is that decimal equivalent, 0.05. Determine the account 10 years after the investment was made, so we know our time is 10. For all of these problems, we're going to use 5,000, 0.05 for our rate, and 10 for our time. Okay. So the only thing that's going to be changing for each of these questions are the number of times per year that they're going to give us interest. So our number of times annually, that means once a year. Monthly means 12 times a year. Weekly means 52 times a year. And daily means 365 times a year. So we should expect that this is the lowest amount that's going to be in our account. Then it gets a little better, then it gets a little better, and the best one should be that final amount, okay? Okay, so let's go ahead and calculate each thing. So F of 10 is going to be 5,000 times 1 plus R to the N. I'm sorry, let's actually put the numbers in to save us space since we don't have a lot of room here. Our rate, 0.05, divided by our N, which is 1, and N is 1, and T is 10, so that's 1 times 10, or 10, okay? So we're really going to get in this first one, 5,000 times 1.05 to the 10th. And then if we actually do that math, I'm going to round it because it's money to the nearest penny. We have $8,144.47 in our account. Great. Okay. Now we should expect the monthly should be a little bit more. So if we do F of 10, I guess we should say this is a T. For our new type of account is going to be 5,000. 1 plus 0.05 to division by 12. And then our power, remember, is the N and the T multiplied together. So our N is 12, our T is 10, 12 times 10. I'm just going to write 120 because then that will make that a little clearer. It'll pop for you, I think. Now, if you take the time and enter that into your calculator, so you might want to try it yourself, round it to the nearest penny, I get $8,235.05. Okay. And now we're going to do it one more time. You'll notice, let's compare. 80-something dollars. It's gone up. We predicted it would go up. Okay. Now let's do for 52. So in this one, it would be 5,000. 1 plus 0.05 divided by 52. And this time, the N times T is 52 times 10, or 520. And then take a second, try that in your calculator. You should get $8,241.63. Guess what? We compare these two, it went up a little bit more, a little over $6. And our final one, for 10 years, given a daily compounding formula, it would still be the 5,000. 1 plus 0.05 divided by 365. And then 365 times 10 is 3650, 3,650. So then you would throw that into your calculator, and it should be the largest of all. And that's $8,243.32. Okay. So make sure you know that formula. Make sure you have it written down. Make sure you have what each one of those variables are standing for. And then if you could go into the calendar, and if you could open up pre-class M46 for me, we're going to do that together now. Pre-class M46, please. So let's go ahead and look at that. So they're going to give you some information up at the top if you want to take the time to read that. It says, let's look at this following. It says, after reading the above text, so that should be everything that we've been talking about, what is important to understand before beginning this investigation? Okay. It says, changing the interval size for a growth factor in financial context will not change the long-term values produced in this function model. So that's a yes. Earlier in the module, our goal in finding partial growth factors was to keep the same long-term value of the function regardless of the interval size we examined. That one is true. The technique for finding partial growth factors in this investigation will be different from the process earlier module. That is true. And we will continue to heavily use radicals to determine partial growth factors. That is true. The technique for finding partial growth factors in this investigation will be the same as the process from earlier in the module. That is not true. I think we're good. Okay. I think that's what we wanted. Let's see. So actually, I think we just want, I don't think we want that one. I think the technique for finding partial growth factors will be different, yes. Earlier in this module, our goal was finding partial factors was to keep the same long-term value of this function in the interval size we examined. That's true. I think maybe just we need those two. The earlier and then the technique, I think, is what we want. Yeah, that's the ones we want. I'm sorry about that. Okay. Now, let's jump to the this problem here about compounding interest. So we have a $5,000 account that is gaining 10% interest every year. Like the first time we gained $500, so you'll notice we've gone up by 500, so 5,500. The next time we gained 550, so it went up by 550, and then 605, and then 665. Okay. So the first block there says if we continue with the example above, during the 5th year, the account will earn how much more in interest? So since mine was 10%, yours might be a different percent, but if it's 10%, since we ended on that 732050. We need that 732050. We're going to multiply that by 10%, and that would be $732.05. Okay, so the account value at the end of the 5th year, because of the fact that we are going to add that interest on, just add those two numbers together. So you probably could even just tell tell iMath that original amount plus 732.05. Okay, and it'll do the math for you. It says each year that passes, let's select all that apply. There's a constant 1-year growth factor in the account. That is true. The account value increases. True. The change in the account value forms a linear relationship. Nope. The interest earns gets larger and larger. True. The change in the account value each year is larger and larger. True. The amount of interest deposited is constant. False. Okay. Now let's take a look at this next one. The answer to part C is true because, let's take a look. The interest earned is always 10% of the account value at the end of the previous year. That one's true. Interest deposited in each of the previous years earns interest in later years. That's true. And then there's a constant rate of change. No. The interest earned is always 10% of the of just the initial deposit. See how they use the word just? So no, that's out. The account value is increasing every year. So I think that's the ones we need for that one. And then we're going to do the same thing again. It says that Loyoso tried to duplicate the calculations from above to reproduce the table, but he kept getting the following results. So what did he do wrong? Do you see how he is continuing to use that 500 from the initial amount? Do you see how we have to keep changing the calculation on the initial amount? So he's calculating the interest each year using the initial deposit. So that's a mistake. That's what he's doing wrong. He is not updating that reference value. He should be doubling the interest. No. He's forgetting that the interest earned in the previous years has to be accounted for because it will earn interest. That's true. And it's multiplying the account value by 0.10 and should multiply it by 1.10. Yes and no. It depends on how you want to think about it. You have to add it on each time. So I believe that's the ones we want there. Okay. So that one is done. Okay, so unfortunately we're not. Please go to investigation 4.7. Please go to investigation 4.7. Now, for investigation 4.7, it is about this number E. So I just need you to go down to where you see this block right here and highlight, please, for me, that E is the constant value that is approximately equal to 2.71828. So I'm going to usually use E as approximately 2.71828. Now, please, when all possible, you're just going to type in an E for iMath. For me, you can use that 2.71828. There's a calculator button above the LN in the light blue color for my blue calculators. For the red ones, it might be yellow, I'm not sure. But I would like to now talk about the applications for an E, okay, which is a little different than what we have seen for our first application, which was a monetary application. So again, this is the 4-7 investigation. Highlight the fact that that E is that 2.71828 value, okay? And then if you could please scroll a little bit more. And I want you to get to this formula right here. And I want you to highlight, please, for me, the word continuously compounding. If interest is continuously compounding, we get what I call, just for silly amount, they call it B. They call it the PERT, or I call it the PERT formula, because it kind of spells out the word PERT. There used to be a shampoo called PERT. I don't know if there still is, but it's a silly way for us to remember that if our function is gaining interest every single second and every single millisecond, you end up getting this irrational number E, that 2.71828 number come up. Remember, E is approximately 2.71828. That number pops into the equation, just like pi sometimes pops into things. E will pop into things, but you only ever use this formula if they say compounded continuously. If they do not use the word continuously, we're going to use the formulas we saw before. Same thing before. T is our number of years. P is the initial amount. R is our rate, interest rate expressed as a decimal. Now, what's interesting about the PERT formula is it does show up in some biological applications as well as financial applications. So it is a formula that is used both scientifically and for budget monetary sort of things, okay? So we're not going to really do the problems from this section. I just need you to jump to now, go to iMath, click on the calendar, find pre-class M47, so we can do that together. Now, this one says that we have a slider. So you should be moving these things here. See, you can increase the rate. You can increase the number of times that it is getting interest. So, play with those. What happens if our rate goes up? What happens if our number of times per compounding goes up? So play with that for me for a second. And then let's talk about the answers down below. Okay, it says the initial deposit of the account is, it is always your starting value, your y-intercept, your vertical intercept. So in this case, it's $2,000. Now, if you move the top slider, remember our top slider was rate. And then it asks us, so what should we fill in there? Okay, let me kind of talk to you through that. I'm seeing if I can pull up the picture for you so I can do the slider with you. Oh, there we go. Okay. So I'm going to pull this over so we can actually see the real thing. Okay. So the initial deposit is $2,000. Okay. it says by moving the top slider, you can change the account's interest rate, that's the R, and it goes from a rate of 4 to a rate of 7 for mine. I don't know what yours is. That's from 4 to 7. Okay. And then it says moving the bottom slider, that's N. Let me scooch this up a little bit. That is the number of times the interest compounds per year. And if I slide it back all the way, it can go from 1 up to 6. Now please adjust yours accordingly. Let's make sure that iMath was happy with that. Oh, I didn't put that in there. I'm sorry, that's 2000. Okay. Now it says, when you move the bottom slider only, which of the following statements apply? Okay. So let's go back. We'll just put that top slider. Sorry about that. We'll just move that top slider and just kind of put it in the middle there. But if you only move the bottom slider, let's start from the beginning to the end. Do you see how it lifts the graph a little higher? Not a lot, but a little bit. So moving the slider increases the initial deposit. Nope, that 2000 stayed there. Moving the slider increases the number of times interest is compounded each year. Yes. The initial account value is constant. Yes. Moving the slider increases the interest rate. No, it does not. Oh, I'm sorry, so don't. So let's submit that and see if that one works. So that's perfect. So that is your 4-7. I don't think there's any other questions. So there you go. I don't think there's anything else they need for that one. Let me check. Ooh. Oh, okay. So now let's go on to the next. There is another question. There's 2 more questions. Let's see if I can preview those for you so we can see those. Okay, let me pull the real thing over here so we can do that. Okay. It says the impact of increasing the number of times that interest is compounded. So if we do interest at 6.9% per year, semi-annually for 2 times a year. So if we do it 2 times a year in that first one, our interest rate would be 1.069. And we would, let's see. I'm thinking how we could find that. Okay, so if it's compounded semi-annually, so you would do, okay. $6.9 divided by 2 is 3.45. Okay, let me put in there 3.45. Okay. But then I have to do it twice a year. And so see how that's 1.070. Okay, there we go. Okay, so I really had to think about that for a minute. Okay, so this one, if you do 6.9 divided by 12, I'm just going to do 1 plus, in parentheses, Mrs. Hawk, 0.069 divided by 12, end my parenthesis. And that's going to happen 12 times, so I'm going to put it to the power of 12. Now, before I go further, let me see if that's going to work. Yeah, okay, so let me do it again. That's 1 plus 0.069, this time divided by 1460. They've given us that number. Thank you, iMath. Okay. To a power of 1460. And that will be our annual growth rate. Remember, we had, when in the notes, we had pulled out parts of the formula. This is the 1 plus r over n t, no, 1 point r over n to the n power. That was the annual interest rate. So that should be that one. And then finally here, let me see if I can make it look a little smaller so you can see it better. I don't know if I can, but I'm going to read it to you. You can see it on your screen. We know that increase in number of times interest is compounded each year increases the future account value. If you were able to compound interest every minute, every second, every million times per second, would it be theoretically possible for you to turn $1,000 into $1 million after 1 year? So there is that formula, that PERT formula. So if we had our $1,000 or our million, I'm sorry, our $1 million bucks. And if we wanted to change that $1,000 into $1 million, that would be e to what power? It always ends up going to an e, and that would not happen in a year's time. E is that 2.71828. That's that continuously compounding. The most you're ever going to get is $2,718. So no, it's not possible to turn it into I think it's this one maybe. Yeah, so what they're trying to tell you here is you'll end up using that PERT formula. If you put 1,000 into the PERT formula and that's e to the 1, it's like 2,700 something. Okay. Anyway, we cut it. That is your 4.6 and 4.7. Thank you. Have a good one.